Okay, so welcome to this video. In this video we're going to be looking at the SACE Specialist Mathematics Exam from 2019, and we're going to be looking at question 6, which is in booklet 1. Okay, so question 6 was a question where we're looking at some 3D geometry. Okay, so question 6 part A, part 1. We'll see question 6 part A says consider the planes that are defined by the following system of equations, and we're given the equations of two planes. Okay, so this is just an equation involving x, y, and z equaling some combination of those terms equaling constant. Okay, so we've got the plane P1 and the plane P2, and what we're asked to do in part 1 is just write the system of equations as an augmented matrix. Okay, so you take each of the equations in turn. You just take the coefficients and you want to do them in the right order, but they're nicely arranged here in terms of x, y, and z. So the first line is going to look like 3 minus 1, 2. And then the augmented part is we're also going to have the coefficient here, so that's a 7. And the other term is, the other equation is going to give us 2 times x minus 1 times y minus 1 times z is equal to 12. Okay, so that's our augmented matrix for this problem. Okay, so that was pretty painless. Part 2, though, what we want to do is go through a process of reducing this so that we can work out the solution to that system of equations and give that solution in parametric form. And we want to show what, or state what all the row operations that we're going to do are. Okay. So the first thing we want to do, if we look at this matrix, is we want to put it into reduced row echelon form. And so we want to have a 1 in the very top left entry here. And so to do that, if we take row 2 and subtract it from row 1, okay, so we get row 1, subtract off row 2, and store that in row 1. And if we do that, what we're going to get is, if we go back here, you can see 3 minus 2, that's going to give us a 1. Minus 1 minus minus 1 will give us a 0. That's quite nice. We want a 0 there anyway. And then 2 minus minus 1 will give us a 3. And the last term is going to be 7 minus 12, so that's minus 5. And we haven't changed the second row. So the second row is still 2 minus 1 minus 1. 12. Okay, so that's what our matrix, our equivalent matrix is after that row operation. Okay, so still we can't do much with this. We need to put it into reduced row echelon form, which means we need to get rid of that 2 in the bottom left entry. And so we're going to get the second row and subtract off 2 times the first row and put that into the second row. Okay, so we're going to have this row hasn't changed. It's not going to change from this row operation because we're storing in 2. So if we get 2 less 2 times 1, that will give us a 0. And then minus 1 less 2 times 0 will still be minus 1. And minus 1 times 2 times 3 is going to give us minus 7. And then it's 12 minus 2 times minus 5, so it's going to be plus 10, so that's going to be 22. Okay, and so we're almost there. We just got a minus 1 where we want to have a plus 1 there in the second entry on the second row. And so we're going to get minus 1 times the second row and put that in the second row. So first row stays like this, the second row just changes sign. Okay, and now we've got it in reduced row echelon form, and we can see we're not going to have a unique solution here because we've got fewer rows than we have unknowns. We've got 2 rows and 3 unknowns, so we're also always going to have an infinite number of solutions, or no solutions at all. In this case, there's going to be an infinite number of solutions, and what we can do is set our parameter z to be equal to our parametric variable t, because we can't really determine what, we don't have a formula that tells us what z is equal to as a single coefficient 1 type entry. But we do have something. The first row is telling us that x plus 3 times z equals minus 5. And if z equals t, we move that 3 times t to the right hand side, we're going to have that x is equal to minus 5 minus 3t. And the second row is telling us that y plus 7 times z equals minus 22. And so y is equal to minus 22 minus 7t, because z is equal to t in this particular parameterization. And so that's a parametric form of the solution. And you can see this is the parametric form of a straight line. Okay, so now interpret your answer geometrically, and we can say the solution x equals minus 5 minus 3t, y equals minus 22 minus 7t, z equals t, is the line of intersection for the planes P1 and P2. Okay, so that's a geometric interpretation. Okay, think of P1 and P2, the two equations that we were solving, as being two planes in 3D, and those two planes aren't parallel and they intersect, and the line they intersect on is given by that parametric solution. Okay, so now part B, we're going to talk about a third plane. So a third plane's been added to the system. It's called P3, and it has a coefficient of the x parameter is 1, the y parameter is minus 1, and the z parameter is minus k plus 2. And what we're asked for is to find a value of k for which there are infinite number of solutions. So we've got the first two planes, 1 and 2, have an infinite number of solutions along that line. And so P3, if we're adding P3, we want to continue to have an infinite number of solutions, and P3 has to be embedded in the plane, the line of intersection has to be embedded in the plane P3. Okay, so what we're going to do is we're going to substitute into P3 the parametric form for the line. So we're going to substitute x equals minus 5 minus 3t, y equals minus 22 minus 7t, and z equals t into P3. Okay, so we're going to get minus 5 minus 3t minus 22 minus 7t minus k plus 2 times t equals 17. Okay, so now let's expand these terms out. We're going to get minus 5 minus 3t plus 22 plus 7t minus kt minus 2t equals 17. You can see if you look at the units that don't multiply t on the left hand side, we've got 22 minus 5, and that's equal to 17. So they cancel. That becomes a 0 on the right hand side. And if you look at the t's, we're going to get 7 minus 3 minus 2, so altogether that's 2. And so it's 2 minus k times t equals 0. Okay, and that's going to be true for all t, so you'll get an infinite number of solutions when k equals 2. So if k equals 2, the left-hand side is always equal to 0 regardless of the value of t. Okay, so that's the case when there's an infinite number of solutions. So this leads to infinite solutions. Okay, and we're asked then in part 2 of part B to find the solution for all other values of k. Okay, so if k doesn't equal 2, to come up with the solution, what we need is for t equals 0. So for other values require t equals 0. And so when t equals 0, then x equals minus 5, y equals minus 22, z equals 0. It's the only solution. Okay, so that's the only solution if k doesn't equal 2. So we get a singular solution. Okay, and then finally in part 3 of part B of 6, they want us to interpret our answer geometrically. And so the geometric interpretation is this, that the point, which is the solution, minus 5, minus 22, 0, is the point of intersection of the 3 planes. P1, P2, and P3. Okay, so you've got 3 planes in space. None of them are parallel to the others, and so the first 2 planes intersect in a line, and then the third plane cuts through that line at a single point. That's the point minus 5, minus 22, 0. Okay, so that was all that we needed to do to answer question 6. If you like this video, then don't forget to click the like button, and if you're interested in seeing more videos as they come up, then subscribe to the channel. And if you've got any comments or questions, then post them below. Alright, thanks very much for listening. We'll catch you next time.